Hello, today we want to show a useful application of this idea of renormalization of local operators that we have introduced on the last video, right? In particular, we want to talk about the phi square operator, right? And its Wilson coefficient, which we usually write in this way, right? And call this by a little bit of abuse of language of a mass parameter, right? We know that we can do a particular renormalization scheme that identifies these with a pole mass of a particle when we have such asymptotic states in our theory, right? And that's fine. In that case, it's very rigorous to call this a mass. But also we have other schemes in which this is a running coupling constant, essentially just changing the shape of the potential for phi square at different scales, right? And this is more what we are interested at this point, right? We are interested in looking at this mass as a running parameter, right? Because otherwise there's no renormalization group equation for it, right? The pole mass is an observable quantity. It does not run, right? Now we're looking at running masses. And one way to introduce these in the theories we have been doing so far, right? So far we have looked at renormalized Lagrangians, which have this renormalization scale parameter, but which are massless, right? We have these massless theories, and we found RGEs for those, right? Now we want to also include these running masses in these equations, right? The way we'll do that is perturbatively, right? So we can actually go from this Lagrangian to one that now includes, so my new Lagrangian now includes also this term, right? Also renormalize at some arbitrary scale m, so both phi and m here are implicitly dependent on this renormalization scale, right? And the scheme I use, right? I can introduce this perturbatively as long as this mass, right, is not big compared to the typical momenta involved in the process I want to describe, right? If the mass is too big for the momentum, so, right? If I define some particular momentum, and this is true, then I really have to resum the mass because the mass is dominating everything. But assuming that's not the case, right, that momentum is at least of the same scale as the mass, then I can do this perturbatively, right, and write my green functions, right? Any green function that now I derive from this Lagrangian will look like a series, a power series in this coupling, right? I'm just doing with m exactly what I do with lambda all the time, right? So I'll define now some objects, which is the green function at zero order in this m square parameter, right? Plus some m square times gn1, which is one insertion of this operator, and that goes on, right? If m squared is small enough in some sense, right, then I can have this series, right? And the full green function will be described as this polynomial in m squared, right, with successively more insertions of this operator, right? So I can go all the way to L insertions of this operator. It's not hard to find a Callan-Symanzik equation for this guy right here, because it's just a generalization of the one we did on the last video, right? For a generic operator, we found out that if I define a green function with n insertions of the field and one insertion of this operator O here, I'll just get these factors of z for the fields in front to the power n, right? And one factor of z for the power for the insertion of the operator at one power, right? And then I get this Callan-Symanzik equation with this new piece right here that comes from this dependence on M, right? Now, if I want to insert the same operator many times, and the operator here is phi square, right? All I get is a bigger power of z here, right? Z to the power L, in fact, for this generic guy. So this equation generalizes pretty straightforwardly to this one, right? Which is just m del m plus beta of lambda. And here, again, I'm thinking of lambda phi 4 and trying to insert mass in that theory, right? Del lambda plus n gamma lambda. And now I have L insertions of the operator, right? Because I'm looking for the Callan-Symanzik for this guy, right? And then I get a power, a factor L here, times gamma of the operator. In this case, the operator is phi square, right? This, of course, is dependent on lambda, right? And this is the Callan-Symanzik for G N L, right? Very straightforward from the previous one. If you're not convinced, then do it, right? Just put a factor L here, see how that changes under a change from M to M plus delta M, and you get this expression here, right? It's the same thing we did a few times already. Right? Now I can do, it's easy to go from the the Callan-Symanzik for G and L to the one for Gn, right? I just have to take this equation right here. Let me copy it. And then I want to save it here. Maybe like that, right? And in this case, I just have now to sum over, I have to sum over L, over N, in fact, right? No, over L, right? This is the expansion I'm doing here, is increasing powers of L, right? N is the number of fields, right? And multiply both sides by M square to the power L, right? This sum comes here, and GNL becomes just GN, right? Because I can write, let me write it here, I can write GN as the sum over L of M square L G N L, which is just the perturbative expansion in powers of M square, right? The only exception here, so this goes through everywhere, is right here. There's also an L here. So in this term, what I'll get is actually a sum over L of L M square to the power L G and L, right? This is, the gamma goes outside the sum, but I have this L right here, so I'll get this term. This is easy to deal with. All you have to do is to see that if I write these in terms of derivatives in M square, so I just write Gn, and I do a partial derivative in M square, right? This partial derivative will come here, drop down a power of L, right? And then I have to keep M squared to the same power, so I just multiply by M squared again. So if I do this, right, I get exactly this, the same result as multiplying by L, right? I can replace this multiplication by L by this derivative. So I can rewrite that equation, right? So everywhere this sum just goes through, right? And in here, before I go through the sum, I just replace this by the derivative, and finally I get an equation which is very similar to this one, but now it applies to Gn And here I have a small change, which is to write this one as m square del m square acting on Gn, right? So you see that having this derivative here will act inside the sum here, and then power by at each power in m square, I satisfy this set of equations. So this one guarantees that all these ones are satisfied order by order in this expansion of m square, right? Because then the coefficients of each power of m square need to be 0 independently, right? And you have this set of equations, right? So that's the Callan-Symanzik equation we're interested right now, right? But we're not so interested in solving for the green function. We won't learn a lot from that, but really to solve for this guy, because this is where I have the information on how the Wilson coefficient of the phi square part is changing with scales, right? But if you think about it, this term right here, right? Since I managed to write this in terms of this derivative, right? It looks more like a beta function than really a gamma function. Not the gamma function itself, right? This is really the anomalous dimension of phi square, but this product, gamma times m square, right? Because if you go back to how we solve this differential equation, right? Just go back to the bacteria, right? In the case we had before, these bacteria were flowing through a one-dimensional tube, right? With velocity given by beta here, right? Now it's like there's two directions, right? Direction lambda and direction m square, right? With two different velocities, one given by beta and the other one given by gamma times m square, right? This one. And that means that the solution to that differential equation will give me a differential equation now for this piece right here, which is very similar to the one I got for lambda, right? So this m square here will have now a running m square, which I'll call m bar square, which will satisfy an equation which is exactly the same as there, right? So we have the log of some momentum over the scale of renormalization, right? And this will have to be equal to the beta function for this variable m, which is this thing right here, gamma of phi square, which, by the way, depends on lambda bar, right? Once you solve everything, everything becomes dependent on the running constant, so you're coupling these two differential equations. But of course, here I also have this m bar square of p, right? And the boundary condition for this differential equation will be, as expected, that m square calculated m is m square, which I had there, right? So you see, for these dimensionful operators that I'm inserting here perturbatively, I did this for the mass, right? But I can do that for more general operators. And it will be true that the beta function for these dimensionful operators depends actually on the anomalous dimension of the operator times something else. So let's try to generalize this just to get a general feeling for what's going on, and then we can even replace the mass by something which is more useful to see, right? So in general, what I'm seeing here in the case of the mass translates into the following statement. If I take a Lagrangian and now I perturbatively include some Wilson coefficients, so I'm starting with a Lagrangian that has only the dimensionless couplings, right? The renormalizable ones. And now I'm adding some number of local operators, each with its own Wilson coefficient, right? The general Callan-Symanzik equation for this guy will be, based on what we did right there, right? Will be this. I just have to generalize for a number of insertions of all the different operators, right? So I have one beta function for the lambda phi 4 part that was in here, or more in general, the dimensionless coupling. I have the same n gamma lambda for the dimension, the anomalous dimension of the field, right? Plus this part, which is written at first as a sum over these various gamma functions times the coefficients themselves times the derivative on the coefficient. Because in each case, I'll do exactly the same I did with the mass here, so that I replace the powers in the number of insertions of that particular operator by this derivative and a multiplication, right? So it's the same I'm doing here, and that acts on a function gn, which depends on a bunch of stuff, right? So you have a number of external momenta, right? N external momenta, you depend on the renormalization scale, you depend on lambda, and you depend on a set of Wilson coefficients, right? And this needs to be zero. So this is the Callan-Symanzik equation for this theory, which I'm obtaining from the ones we had before, but now I'm inserting perturbatively these any operator essentially, right? But I can improve that, right? We already seen that this is a gamma function times something, but it looks a lot more like a beta function. Now I have now my bacteria are living into hyperdimensional, high dimensional space, right? They're already science fiction bacteria, right? And I want to write all the velocities in this multi-dimensional space more explicitly. The way to do that is to remember that the important thing here is the dimension of the operators, right? We have done this many times. I'll define again some symbol, which I'll call di, for the dimension of the operator, right? And then I'll use that to rewrite the Wilson coefficients, right? So I can take any of these Wilson coefficients, Ci, right, and rewrite by defining a dimensionless number, right, rho I, times, and then I can use any scale here, but I want to keep my equation simple, so there's no reason to choose any other scale other than this one, right? And I'll put this 4 minus the dimension of the operator, right? I'm here still in 4 dimensions. That's why the 4 here. Otherwise, I would have a d here for the number of dimensions of space-time. So that guarantees that these guys are dimensionless, right? Because I'm putting all the mass dimensions in these here explicitly. And now my Lagrangian, this Lagrangian up here, right, gets rewritten in terms of this rho I, right, in this way. Four minus di, operator I, right? Bring this I up here, we have to remember this is the renormalized one. It's also dependent on M. Right? So now I'm working with this new Lagrangian in which I wrote all my couplings in a dimensionless way, even the mass, right? I have to be careful though, because by doing this, I'm inserting an explicit dependence on M, on the Lagrangian. And now this derivative, when acting on green functions, will pick up this new dependence on M, right? So I need to be careful in compensating that in the Callan-Symanzik equation, right? In order to see the effect of having this coupling there, remember that in when we were, solving these these green functions, these Callan-Symanzik equations, right? We used the fact that for some green function that we were solving it for, right? All the dependence on M was coming from some counterterm. So somewhere I had a counterterm with some number of external legs, right? And I had a function here of this renormalization scale, right? Now I will have a new contribution to that coming straight from the endpoint vertex that involves, I don't know how many external legs here, but that involves this coupling, right? This will be proportional to rho I times m to the power 4 minus di. This will appear explicitly now in this green function with n external points, right? And that means that when I do the derivative, this derivative, on that green function, right? I'll pick up this dependence explicitly, right? And this will be proportional to 4 minus di, right? Times rho I m 4 minus di, right? Because I have an extra power of m here. This needs to be compensated in my green function because in the end, any dependence on m coming from this derivative needs to be compensated by the same thing coming from some other piece so that this is still 0, right? And that I can compensate in this piece, right? Just notice that if I do di minus 4 rho I del rho, notice I'm exchanging the Ci del Ci by this, right? That's my point. I want to exchange the dimensionful Wilson coefficients by dimensionless rows, right? And I act that in the same green function, right? When this acts on the same vertex, right? It will now give me a di minus 4, right? Now I'm differentiating in rho, right? So I'll get m4 minus di, which was already there, right? That depends a lot on which power of rho I have here, right? But in the end, I'm multiplying by rho again. So this will be proportional to the same power of rho I that I had here at start. In this case, just rho I, right? So that means that these two, you see the opposite sign, these two compensate. So the proper way of exchanging this equation by one involving this rho I is to include this extra piece right here, right? So with that in mind, I get a new, let me copy the old one so you can compare. I don't care about these dependencies. Let me just put it down here. I can delete it later, right? Our new Callan-Symanzik equation will be this one, m del m plus beta lambda del lambda plus n gamma of lambda. So far so good, no changes, right? But now this piece will become a sum in I of gamma I lambda plus this thing, di minus 4 times, right, this piece right here, rho I del rho I. And this thing eliminates the new terms that will be coming from here once I act on the green function, that now explicitly depends on m, right? So there it is. This is my new green function, right? So this piece changed consistently into this one, right? Let me put a box around that one. And then now there's even an extra step I want to take to make this thing we're seeing right here, right? Not the box, really, really explicit, right? I want to define now a set of beta functions in the following way, right? I can define now a set of beta functions which will be given by di minus 4 plus gamma I times rho I. And these I can replace here, right? Just copy that equation down here. And I get pretty nice expression. Beta I. Delete the box for now, just to put things in a nicer way. Okay. And now things look really symmetric, right? You see that once I write my Lagrangian in terms of dimensionless, these dimensionless couplings rho here, right? There's really no difference between this part and this part, right? All of them will have their own beta functions. Everything is coupled, of course. So if I write the RGE equation for any of these dimensionless couplings, including lambda, right? It will look like this, right? Some momenta over m. Now I have to be really careful, you too, right? To not to confuse my p's with my rho's. They can be really similar if I'm not careful. This is p, right? And I'll try to exaggerate the rho. Rho I bar is equal to beta I, which now depends on every rho, right? So I can put a set of all rho here, and lambda. And by the way, the equation for lambda bar will also depend on the rho. This can be really complicated, right? Unless you are in the perturbative limit, where you can linearize everything and just take one coupling at a time, right? And avoid cross terms. But it could be really complicated to solve these equations because you have a lot of coupled solutions for them, right? So you see, this is a very nice explicit way of seeing what's going on for these theories. Of course, solving this differential equation at leading order is much simpler, right? You just have to look here, right? So I said all these runnings are coupled, but that happens through these gamma functions here, which again can happen, can depend on many couplings, right? So this is something like, I could write it like this, di minus 4 plus gamma I, which depends on everything, all the set of rho's and lambda, right, times rho I. But since I have a explicit dependence on one of the couplings here, the term that involves gamma, I'm going to put a second bracket here. This is like that, right, because there's a big one here too. The product that depends on rho times gamma will at least have 2 powers of couplings, right? Because this is It's not a number. It appears once I turn on the couplings. So at leading order, I can ignore this part right here and just write beta I is equal to di minus 4, right? We did this many times before. Essentially what I'm doing is that in the leading order, what dominates is the scaling with the dimension of the operator. And if I plug this leading order beta function here, I can solve this differential equation, right? For this case, it will become just a simpler d log. I won't repeat the argument of the log for now. Right? Rho I bar is equal to di minus 4 rho I bar, right? Just using this beta function here, right? And that one has a simple solution, which is that rho I bar is equal to rho I with the usual boundary condition, right? Rho I calculated m is equal to rho I, this constant right here, but that's just the momentum. Let me draw the momentum like that so we don't get confused, right? To the power di minus 4. And that's actually something we said in many times before, right? In different ways. But again, you see that the operators that have dimension smaller than 4 will be important at low momenta, right? And the ones that have dimensions bigger than 4 will be suppressed by this power at low momenta. And the expansion is in powers of p over this arbitrary scale here, right? But in any case, if you go below that, you see a suppression, right? So that's again the classification of relevant, irrelevant operators coming now straight from the equation of the running, right? Of the dimensionless couplings, right? Now we'll be interested in studying. So now I want to specialize the story a bit, right? I want to look explicitly at lambda phi 4, right? I want to look at a massive lambda phi 4. I'm introducing the mass, right, in this way. So I'm defining now dimensionless coupling for the mass using this kind of language. So I define now a dimensionless mass coupling in this way, right? Just using this definition right here, right? For the case where the Wilson coefficient on the left here is just the mass square, right? And the dimension of this operator is 2, right? So you get that relation, right? But I want to generalize a little bit to d dimensions. So I'll go from 4 dimensions to d, right? That's pretty simple to do with most operators. I just have to replace these 4 you see going around here by d, right? But now I have, the last thing I had that set the lambda coupling apart from the rest is gone, right? In 4 dimensions, this is straight away a dimensionless coupling, but in d dimensions, it is not, right? You have to remember that in d dimensions, the dimension of the scalar field is d minus 2 over 2. That means the dimension of phi to the 4th operator is 2d minus 4, and so the dimension of lambda is 4 minus d, right? And that means that I will also redefine lambda into lambda prime m 4 minus d, like I did with the other coupling. So my lambda prime now is some rho, I could call it just rho 0, right? But I'm not putting a lot of couplings, right? Just this one in the mass. So I'll keep calling it lambda, but keep in mind I'm keeping this lambda dimensionless by doing this, right? And that means I have to compensate in the Lagrangian by a new definition of the beta function, right? As far as the mass is concerned, right, we know that the dimension of phi square is d minus 2, right? And that means that this term, rho m, now in d dimensions, minus d minus 2, which is the definition I'm using to do this, right? Phi square continues to be rho m square phi square, right? So nothing changes, right? This was my m square. So nothing changes with the redefinition of mass once I go to d dimensions. That's something we already knew from before, right? Too, because the mass is always a relevant operator. It does not depend on the number of dimensions, the scalar mass, right? So finally, what I'm talking about is that I'll, from this point on, work with the following Lagrangian. So this is just the kinetic term, the free Lagrangian, right? I'll work with this Lagrangian in 4 dimensions. I have this piece, rho m, which is now my mass coupling. Won't delete m square phi square. Remember, these are the renormalized field. And then I have a 1 over 4 factorial lambda, dimensionless lambda. I won't keep carrying this prime, but keep that in mind. M4 minus D, phi 4m. And maybe at some point I'll be interested in including other stuff, but this is the core of what I want to calculate, right? In the last video, we did figure out the counter term for this operator phi square, right? But we did it in 4 dimensions. Now I want to generalize this, right, to d dimensions. So my counter term was proportional to, let me put it like that because I'm not writing the full counter term. I'm only interested in the parts that are dependent on m squared because I want to solve for the running, right? And so we had a gamma of 2 minus d over 2, right? This is a calculation we have been using for the whole course. Right? This is nothing but this loop. And as I go to 4 dimensions, I can expand this guy, right, as a minus 2 over epsilon, or d minus 4, minus log of m squared, right, plus a term proportional to epsilon, d minus 4, times a bunch of stuff, right? Do I care about this part? Yeah, I want to write it explicitly, minus 1 over 4, ln square m squared minus half gamma, not the gamma function, right? The Euler gamma, ln the log of m squared plus other things, right? What I have here is terms that which are independent of m squared, and that includes the famous mu square term, which I'm ignoring again. I don't want to be worrying about this guy because the scheme I'm using, I can get rid of him, right? And also higher orders on the d minus 4 expansion, right? This is all there, right? And now I can take the derivatives, right, in m squared. And I'm trying to keep this linear term here. That's why I went to higher powers, right? You see pretty soon why. So now I want to know this partial derivative, which is what matters for my Callan-Symanzik equation of this guy, as I go to 4 dimensions. This goes away, right? This first term gives me a -2, right? Just differentiating m squared. And then I have a correction, which is d minus 4, Euler gamma, and the log of m squared. Right? This is just differentiating this whole thing in terms of m squared, right? Plus other things which are order epsilon squared, right? So d minus 4 to higher powers. And now this is interesting because this part right here is exactly what we had in 4 dimensions, right? And I found a correction to it as I go away from 4 dimensions, right? And so I can write now, remember, now if I want to get my gamma function, right, for phi square, I have to use this counter term and the fact that the gamma function of phi square is just m del m of minus the counter term, right? And remember, here I just wrote a part of the counter term. The full counter term is this, right? So there's an extra factor in front here, right? Besides this part that depends on m, right? This will give me a fairly straightforward expression for the gamma function, right? One piece is just this -2 multiplying this, which is lambda over 16 pi square. Remember, there's also a minus here that compensates for that minus, right? Plus, again, the same factor multiplying this, right? Which multiplies this d minus 4 part. For now, it's just a fairly simple expression, right? The important thing for us is that this is order lambda times d minus 4, which are the two expansions we're doing here, right? We're expanding for epsilon, yeah, right? To get the correction when you go outside 4 dimensions, right? And we are doing the perturbative expansion in lambda. This is a term which is linear in both, and that's the leading order correction, right? We can even rewrite this in this way because again, this part is the same we had in 4 dimensions exactly. This is the correction, right? And one way of indicating that is by defining some gamma of phi square 4, where 4 here is the result in 4 dimensions, and this is the correction, which is easy to calculate, right? Just have to multiply this thing by lambda over 2 times 4 pi square, right? So that's the expression we get. Now we can plug this into the definition of beta, this one right here, right? Let's do that. So in d dimensions, beta I is just di, the dimension of the operator, minus the dimension of space-time, plus gamma I rho I for any operator which I'm labeling by I, right? In the case of the mass, this is the beta mass, right? Which is equal to 2 minus, and I will rewrite this. I want to group this thing, so I just for now write this as d minus 4 plus 4, right? Plus this thing, gamma m or gamma phi square, which is this, right? So write this in terms of gamma 4 of phi square plus something of order lambda times d minus 4, right? And that I can reorganize now in the following way, right? I just take these 4, add here, right? And there's a minus, there's an extra minus here, right? So that gives me, of course, this is all multiplying also rho m. I forgot the rho m right here, right? So this gives me this 4 together with this 2 is just a minus 2 here, plus this part minus d minus 4 straight from here, right? Plus something of these higher orders, right? Now I have a term which is I can be linear in lambda, right? This guy right here is linear in lambda, right? I have this part which is linear in d minus 4, but I have products of these two which I'll eventually forget, right? So see what I'm going for here. I have to compress things a bit because otherwise I'll have no space for rho m. But you see what I'm going for here. I'm going for linear corrections in the coupling and also for linear corrections in the dimension, right? In the change of dimension. So now if I disregard, right? If now I take lambda times d minus 4 going to 0. So any double correction here goes to 0. Same for the other row. Rho I times d minus 4 also going to 0 because there's one here, right? Then I can write my beta function in a simple way, right? It will be just minus 2, but that's a heavy-handed approximation, right? Rho m plus whatever. Then this correction also goes away because of this. Same is true for other functions. I could easily repeat this for any beta I, right? And write this expression here, right? Just replacing gamma by gamma 4. I'll bring back this correction if I need it. Right? But this already tells me how this dimensionless mass parameter runs, right? At leading order, I can ignore this because, again, this is a product of two coupling constants, a linear thing in lambda here, a linear one in rho m here, right? If I ignore this part, then things get really simple. This the differential equation for rho bar will just be with a beta which is minus 2 times rho, right? And that means that rho bar m will be some constant rho m times the momentum over the scale to the power minus 2, right? Which means that this increases for low momentum as the momentum square, right? So that's how the mass grows, right? And it's the usual thing we expect for masses. They go as momentum square, right? There's one more thing we can get from this approach, especially because we went away from 4 dimensions, right? We're still in lambda phi 4, but we went away from 4 dimensions. And now we have a mass around, right? We can show that the mass, at least at leading order, does not change too much what's happening for lambda. and check a result we got way back in the case of the Wilsonian renormalization group equations, which is this non-trivial fixed point for lambda phi 4, right? So now we changed a little bit our definitions for lambda, right? So our green function, just think a little bit on the 4-point green function. Now it will be proportional to lambda, the adimensional lambda, but now we have this explicit dependence on m, right? Because we want to make this guy adimensional, right? So our green functions are like that. And that means that once we do these partial derivatives in m, right, and the derivative in lambda, right, these two things have to cancel each other. Same we did with the other local operators, right? But now these will become, if I focus only on the cancellation between these two guys, right? The green function has this term, so acting with this derivative here, I'll get lambda times 4 minus d m 4 minus d, right? This is the effect of these derivatives acting on this green function, right? But now the effect of this one will be to get me a beta times m to the power 4 minus d, right? And of course, this is the leading order contribution to G4. There are higher orders here, right? And since I don't know exactly at what order beta is appearing here, I just write this like that, right? And this needs to be 0, right, in general. I have to have a cancellation of these three parts. That means that the beta function now in outside 4 dimensions, right, the beta function for lambda will be, I'm just solving this, right? So I multiply both sides of the equation by divide by m to the 4 minus d, right? That eliminates m, this power from here and here, but it ends up multiplying higher order terms. So beta is equal to d minus 4 lambda, which is this part, just passing to the other side, right? Plus m d minus 4 times these higher order corrections, right? Now I have to expand this guy, right? So beta will be this piece times, now I can take this little piece here and write as a 1 plus some correction, order d minus 4, right, times this, right? And do the usual assumption that order d minus 4 times order lambda square is 0. But this 1 times order lambda square is exactly the beta function I had before, right? Because this is a correction when I go away from 4 dimensions. And this part here is just, so this 1 times order lambda square was my beta function in 4 dimensions, right? So this is the correction for going away from 4 dimensions. So what I'm getting at here is that my new beta function will be this d minus 4 times lambda. This is the term that is the lowest order correction as I go away from 4 dimensions. And this guy is my beta 4 that we know for lambda phi 4, this guy is, right? So this beta 4 here, we have calculated this guy before, is just 3 lambda square 4 pi square. So you see, I'm allowing d minus 4 times lambda to be of the same order as lambda square, right? That depends a lot on my choice for d, my choice for lambda, right? But now I can use this, right? This new beta function to think about fixed points. Let me write it again in this way, because I'll be going below 4 dimensions, right? And if I am below 4 dimensions, this number is positive, right? Which means this whole term is negative, and that is working in the opposite direction that this one, which is positive, right? So what I'm saying here is for d bigger than 4, right? I am guaranteed to have beta positive and nothing interesting happens, right? Just lambda goes to 0 as the momentum goes to 0. But if I have lambda smaller than 4, then these two things work in opposite directions, right? I'll have a beta function that at first, let me draw it nicely, right? This is something we saw before, but not in this language, right? Before we did this once, but we were using these discrete momentum shell integrations in the Wilsonian approach, right? So the whole fixed point seemed to depend on this parameter b and all of that. Now I just have the beta in terms of lambda, right? I see that at first, right, this term wins, right? And you have a negative beta function. In fact, this term wins, right, for small lambda, because d minus 4 is fixed as I change lambda. So at first, beta function is negative, right? But eventually, the higher order corrections kick in, and you bring it down. And there's a special point here where these two parts cancel each other, right? And it's easy to solve for that. I just look at where my beta function is 0 and solve. And this lambda star is equal to 16 pi square over 3, 4 minus d, which is exactly what you get from the Wilsonian approach. If you demand that those two contributions cancel each other, and then you spend in order to get the linear contribution as I go away from 4 dimensions in the three-dimensional systems direction, right? I'm going below 4 dimensions. This will be pretty useful because we'll use this fixed point to look at some condensed matter systems on the next video. And this fixed point allows us to take a first look at critical exponents, right? But that's for the next video. This is the message for today. Thanks.